Hello and welcome. In our sequence of videos on data pre-processing, today we are going to take up missing values, the most common problem with almost all the real-world data sets. So let's learn this step by step. What are we going to cover? We're going to cover all about missing values, starting with what are missing values, why to perform missing value treatment, choosing appropriate missing value treatment, common mistakes to be avoided. So do watch this video till end to understand how you can avoid those common mistakes. And of course, we will be doing hands-on in Python, which demonstrates clearly how different techniques can be applied for missing value treatment. So this is a complete package which will take you from a beginner to an advanced user when it comes to missing value treatment. And before we get started, if you've not already subscribed to this channel, you might want to do that. We'll give you enough substance through our videos that'll convince you that this is the right place to be at. Let's get started. First of all, what are missing values? Let's look at some data. So missing values are not just the blank cells. In fact, in this data set, if you see, all these cells marked in red are missing values. So let's look at a column called age. Here, we are supposed to capture the age in years. But what we have at few places are these hyphens and these hash marks. Should we consider this to be a missing value? The answer is yes. Similarly, the column called new role, it's supposed to have zeros and ones, but we have a question mark here. Is that a missing value? Yes. Team size, yes, it has a blank cell, which is of course clearly a missing value, but writing NA in a team size is also a missing value. Similarly, writing null in a column called rating is a null value. And in sales, let's say we put NaN, which stands for not a number. That's also a missing value. So missing values are not just the blank cells. If you have an entry in your data which is not appropriate for a particular feature, that'll be called a missing value. So labeling all these values as missing values, let's understand why do we want to perform a missing value treatment. Let's take a hypothetical scenario that somebody is in need of money, and this person would approach a bank. Do you think the bank would be able to make a decision on loan amount eligibility without considering the current income of the person? Why would a bank want to know that? Bank would always be concerned about knowing the current income because bank wants to know whether this person who is a borrower is worthy of that loan or not, and whether this person would be able to pay back as per the commitment or not. Otherwise, this person might just borrow the money and waste it without even bothering about paying back. And the bank would run into trouble if many people do that. So the bottom line is that in the absence of data, our decisions become less reliable. We need some information to be able to make decisions. And certain pieces of information are very critical. We just can't afford to miss them. So is the case for a model. When your model is trying to make a decision, it needs certain inputs. If we don't supply appropriate inputs, we can't expect the model to make the right decisions. Therefore, we need to perform missing value treatment wherever the data is missing. Coming back, let's assume this is our data and we have more rows. We are just looking at a snapshot of this data. If we were to ask you what is the right treatment for missing values, almost 95% of the people would say we can replace the missing values with the median or the mean or maybe something else that we understand the best from our knowledge of the subject matter. Well, that's not the actual starting point if you're solving a real-world problem. Before you make any assumption and start treating the missing values just like that, the first thing to check would be with the source. Don't make assumptions. First, check with the source if they can provide you the data. If you're working with a client who has supplied you this data, it is your duty to go back to the client and tell them that there are some missing values. Is there a way that you can fetch this information? And trust me, your smartest guess would not be as reliable as the actual information is. So don't blindly jump into missing value treatment with any approach. First, check with the source. If possible, can they provide you the data? And if there is a denial, then you can look for alternative treatments. Now, is there a problem with the mean and median approach? We'll discuss that as well. Let's understand what are the common mistakes that people make, especially with the common choices like mean and median. Let's just concentrate on these two columns. Let's say we have a column called team size and we have a column called sales, and sales column has a few missing values mentioned here. We don't know what these values are, and we don't have visibility to anything else. For the time being, I've blindfolded the team size column as well. And we have more data. This is not the total data that we have. We have more data, more rows follow. It's just that we can't show it here. So let's say you calculated the median of the data and found it to be 106,000 and the mean of the data, which is 110,000. Let's say you choose to replace these missing values with the mean in this case. So you got the mean of 110,000 at both the places where the data was missing. So far, what we've done is we've only considered the sales column, as if this column exists in isolation. It doesn't get affected by anything else. What if I were to reveal the team size to you, and I was to tell you that as against the normal team size of 12 to 15, this particular value is 25, and this value corresponding to this missing value is just 5. Don't you think this is a much smaller team size, which probably doesn't deserve the average of the overall data? And don't you think this is a much larger team size? We could easily expect it to be doing maybe double of what we are seeing here, because the team size is much larger compared to the common team size. So how would an average justify this outcome? The question is, then what is the alternative? Well, if we have more data, can we try to find out observations which are similar to this team size and do something about it? Or can we find out observations similar to this team size, which is just 5, in somewhat proximity to this value, and try to find out what the value here should be then? So the point we are trying to emphasize is that features don't exist in isolation. It is not that the sales is existing as an independent feature. It may have an effect of the team size. If there is a bigger team supporting the sales of the same products, you could see bigger sales numbers. And if it's a much smaller team, you could see much smaller sales numbers as well if you're dealing with the same products and services. Let's extend a little bit on this idea of finding out similar observations. So here's our data. Let's start from scratch. This time what we are going to do is we are trying to look for the observations where the team size is comparable to 25 and the team size is comparable to 5. Let's see. We found some observations and we've put it in 2 separate tables. So we found another 4 observations at least where the team size was comparable to 25, something in the range of 23 to 25, maybe a little more like 26 as well. And similarly, we've taken the observations where the team size is same as 5 or maybe 6 or 7, but it's still in the close range. The team size is not close to 12 or 20 here, and the team size is not close to 5 or 7 here. Don't you think if we take the comparable team sizes now and take their average and put it here, that will be a more justified imputation? Well, that indeed would be. So let's say we take an average of the available values where the team sizes were comparable. Now you would realize that instead of that 110,000, a better value here would be around 186,250. Similarly, compared to an average 110,000 that we had put here earlier, looking at the overall data, a better value to put here would be something like a 69,750. This is a neighborhood-based imputation that we've done. And these can be easily achieved using the algorithms. Now we're going to take you to the hands-on piece. We'll pick up a popular data set, which we've modified a little bit to be able to show you missing value treatment. But on that data set, we'll perform every single step, right from the basic treatments of mean and median to the advanced treatments which use imputers. So stay put and continue to watch this video till end. There's a lot coming your way, which is important for you to know. All right, so we are at the Google Collaboratory, and we are taking up a very popular data set known as the Vine data. This has been obtained from UCI Machine Learning Repository. If you're not familiar with that, we'll provide you a link in the description where you can get the dataset from. I've already pointed to the data source, and we will just get started. This is a slightly modified version of the data because the original data did not have missing values, so we had to introduce the missing values. But this is still manageable. We begin by importing the common libraries like NumPy, Pandas, Matplotlib, and Seaborn. Pandas essentially to work with data frames, Seaborn and Matplotlib for visualization. And if we have to work with arrays or missing values, which are generally represented as np.nan, we will need the NumPy library as well. So let's just import these libraries. Now we are ready to read the data using Pandas. We are using the read CSV to get the data set. We finished reading the data. We may first want to check how big is the data, how many rows and columns are there. So we're running df.shape. It has 178 rows and 13 features. And let's just check the first few rows of the data. So we can do it head, and we are checking the first 10 rows of the data. That's why we passed a number 10 here. By default, it shows us the 5 rows. As you can see, in the column called alcohol, you already have a few missing values, which are represented as nans. But notice I mentioned in the theory video, these may not always be just nans or not a number. These could also be values which are represented by peculiar characters or special characters like hash or @ or question marks or a mix of these. So one column seems to have some missing values, and we are looking at only the first 10 rows. So maybe there are other features as well, but we can just glance through and we can see that maybe there's another column called proline, which seems to have some missing values. This is just based on the first 10 observations. There may be more missing values. Let's run descriptive stats on this data, and this would tell us the 5-number summary and things like that. Let's quickly do an info, which means we want to check the data types, and it shows consistently that our data is float type. All the variables are numerical, seem to have decimal digits. And it also gives an idea that alcohol, for that matter, has only 158 non-null values, which means it has about 20 missing values. And likewise, this column called proline has 163 values, which are non-null, which means if you subtract this number from the overall number of rows, you'll get 15. So it seems this column has 15 missing values. Notice when you get special characters in any numerical feature, the data type as read by Python changes. Python begins to call it an object type. So it means other columns in our data do not seem to have missing values. Only 2 columns have missing values. We'll further check this with the help of isnull.sum, a couple of cells down the line. We can also check what all features do we have by doing dataframe.columns, and it gives us the list of features here. Let's check isnull.sum, and this would tell us feature-wise how many missing values are there. So in a way, we already assess that here through info, but this makes it further clear that alcohol has 20 missing values and proline has 15 missing values. If we want to check the percentage of missing values in each column, we can divide this isnull.sum. That's what we did here, multiply it with 100 to convert it to percentage and divide it by the index size. And whatever is the output that we get, we are rounding it off to 2 decimal places. Finally, the output will also be sorted in a descending fashion. When we put ascending is equal to false, it's going to give the output in a descending fashion. So we'll get the column on top, which has the highest percentage of missing values. Let's do that. So you can see alcohol has 11% missing values and proline has 8.4% missing values approximately. An interesting thing to check here would be how many unique rows in our data contain missing values. And in order to do that, you don't have to do much, but you have to just give an additional input to isnull.sum. You just have to write axis is equal to 1. It'll tell you how many unique rows have missing values. Note that may not always be the addition of the missing values in both the columns, because a particular row could have more than one missing value as well. Let's check. Well, in our case, it seems that these missing values are uniquely present in different rows. That's why the number 20 plus 15, we got 35 rows with missing values, which means in our case, these 35 rows have just one missing values. Had some of the missing values from alcohol and proline been overlapping in some of the rows, we would have got a lesser number here, but that's fine. Now, if we want to get the index of those missing values, see, it may be easy for us to visualize everything here because we're dealing with a much smaller data set. But in a real data set or a large data set, you may want to check what all rows contain missing values. So can we get the index? So what we are saying is that we want to filter out such rows which contain any missing values. And we want to get the index of those missing values. So these are the indices which represent the rows that have missing values. Now, if you wanted to check specifically for what all rows alcohol values are missing, we can write that filter only for the alcohol column. So we are checking for the location of the alcohol column where we have a missing value. This gives us these indices, and likewise, we can check it for proline separately. These are the indices. Notice both of these together would be forming this. That's the indices belonging to missing values in the overall data frame. An easier way to visualize this could be using a heat map. So what you can do is, to the heat map, you can just pass an input, which is df.isnull. Isnull is going to give a Boolean output in terms of true and false. We've chosen a color map, which is cool, warm, and we don't want to see a grid because we have only 2 values. Let's see how this output looks like. So you see, this is your entire data frame, a snapshot of your entire data frame. And these red markers that you see here in the column called alcohol and proline basically represent the places where you have a missing data. Why do we have only 2 colors here? Because isnull would only return true and false. And it is chosen wherever there is a missing value, true, it's representing it by a red color in this case. So we get an idea there are 2 columns which have missing values. Just another way to look at it, you could have had more missing values and multiple columns. This will come pretty handy on a large data set as well, because it straight away gives you a snapshot of the overall data. Let's move to the missing value treatment now. And like I said, while we criticize the common treatments and I explain the reason why it's not right, let's go through the sequence because many of you might be learning it for the first time. So first we are doing a copy of the original data frame. Because we are going to try multiple treatments, At all stages, we'll create copies of the original data frame and not affect the original data. So we are saying we'll simply choose the easiest treatment first of all, which is that we want to drop the rows containing missing values. This, of course, leads to loss of data, and you may apply it only when the percentage of missing values in your data are very restricted, are very limited, and they do not affect the overall quality of the data. So if your data has missing values in the range of 2 to 3%, and it is not following any specific pattern, what I mean to say is that these values are missing at random, you can simply choose to drop those rows. This can be achieved using the method called dropna, which is, as per the name, going to drop the missing values. Axis 0 represents the rows, and in place is equal to true means this change will be effective on df drop, which is a copy of the data frame. So we can easily do that. And then we are checking what is the output. Original data frame had 178 rows. How many rows will be left with? We'll check that now. We're left with 143 rows. 178 minus 35, that was the total number of rows we counted, had missing values. All 35 rows have been eliminated. Probably not the best treatment for this kind of data because the percentage of data that we have lost is pretty high. Then let's move to doing the missing value treatment with some specific values. So you may estimate the value using some central tendency, or you may have some knowledge about the domain where you bring the value from. Once again, we are creating a copy of the data frame and we are using the fillna method. So there are multiple methods in Pandas which allow you to do these treatments. Attached to the data frame, the fillna method allows us to pass a specific value. We are passing a median value here, and we are saying we'll do it as in place is equal to true. Now, you might want to see how these values look like. So remember, some time back, we found all the indices which contained missing values. We are saying we just want to have a look at these two columns for these indices where we are doing this missing value treatment. Let's see how does the data look like after doing the missing value treatment. So if you see, we chose the median and the column called alcohol, these indices which had the missing values here, 0, 5, 10, 14, and so on, these have got a constant value here, which would have been the median of the alcohol column. Likewise, if I scroll down, you would find that for proline, we seem to have put 630 here. These places in the data earlier would have had the missing values. And since we have chosen the median, that's what we have put here. Let's check if this is the median. So yes, you can see the median for alcohol was 12.865 and the median for proline was 630. That's why wherever you had missing values, you have put these values. Now these values were not missing. That's why these are the original values. Likewise in proline, the values earlier were available and that's why those have not been touched. Only the places where you had some missing data has been modified. Moving forward, we have choices like forward fill and backward fill. Not very useful for data where the rows are independent of each other. A row is a different observation. This may be useful when you're working on the time sequence data, but let's see how do we actually apply it. So let me show you the original data frame. This is the data frame where we have some missing values. We saw that earlier as well. And once again, a missing value here for proline, as you can see. And if we do a forward fill is simply going to take the previous value and copy it to the cell where the value is missing. So for example, here, if we have a nan and the previous value is 600, it's going to paste a 600. But the problem would be that for the first observation, if you have a missing value, it doesn't have a previous entry. So for such cases, you can do a backward fill, which means it'll take the subsequent value and copy paste it here. The point is, this may not be the best treatment unless you have the reasons to believe that this is how the data progresses. And like I said, that may be more meaningful for time sequence data. But let's try how this works. So we are making another copy of the data frame, df forward fill, and we are applying forward fill. Let's look at the output of the forward fill. So of course, as anticipated, this value didn't get changed because it didn't have a prior value. But this value here, which was missing, got 600 because the previous value was 600. So to cure this, we will show you a backward fill. Exactly the same way, applying the backward fill method in place is equal to true. And now you see, for this missing value, we got the subsequent value, which is 14.21 pasted there. Moving on, the next approach is to treat the missing values using an imputer. We have multiple options under imputers, and Scikit-learn, which is the backbone library of machine learning, has a lot to offer when it comes to missing value treatment. SimpleImputer is one of the easiest imputers, and we'll be telling you about some interesting imputers after this. So let's make a copy of the data frame. And a simple imputer requires us to pass an input which says the strategy. So if our data does not contain extreme values, we can safely go with a mean also. Remember, sometime back I criticized using mean, but that's still the common treatment that most of the people learn and know, so I'm just showing it to you. Simple imputer syntax is a little different. So you have to instantiate it, and then you have to fit it to the data, and then you can do a transform. In a single step also, you can do fit underscore transform, or you can do it in 2 steps. So we are fitting, which means we are letting the imputer assess the data for the mean values. And when you do transform is when the actual change happens. Now, whenever you do an imputer, it changes the data to an array format. So in order to restore it back as a data frame, we'll have to pass the imputed output and mention the names of the columns. Finally, we can filter out those specific rows where the values were missing. This is the same index list that we created above. So we will look at the alcohol and proline columns after this simple imputation with the means has been done. Let's run this, and you can see the first few values here, alcohol, because we are only looking at the rows which contain missing values. The first few rows here that you see primarily belong to the alcohol column where you have imputed the mean. And the last few rows here, as you can see, represent the proline column where we've imputed the mean again. Likewise, if we would have wanted to impute the missing values with the median, we could have done that. Notice I showed you another method to do this, which was through the fillna method, but SimpleImputer also accommodates different strategies. We can choose to put median here, exact same syntax as we followed above. So this would show us that 12.865 as saw earlier, and it'll show us 630 for proline as we found through the median calculations. Now, if you have reasons to believe that you want to put a specific value, let's say you want to put a value which you know is the right value, and you don't want to put a mean or median, you can do that again through SimpleImputer. We are saying that we want to fill a value which is a constant, strategy is a constant, and the value that we want to fill is 0. Now, wherever in your data the values were missing, it'll put 0. This is just an instance, an example to show it to you. The code is exactly the same as it was shown earlier. So what we have done is that we are instantiating a simple imputer, doing a fit, doing a transform, converting it to a data frame, and then finally displaying only those rows which got affected with this treatment. Essentially, the ones which contain missing values. As you can anticipate, the first few rows for alcohol have all got zeros because that's the constant value we chose. And the rows belonging to proline, which had missing values, have all again got zeros because that's the input that we passed. Now coming to a relatively advanced imputer, which is known as the Cannon imputer. And essentially, this is what I was hinting at when I said in the example data set, we may want to look for similar observations in terms of team size before we decide the sales values. So Cannon imputer, as the name goes, is K nearest neighbors based approach. We've done a detailed video explaining Cannons. If you need more clarity on the Cannon algorithm, you can refer to the description. You'll find a complete tutorial on Cannon as well. That'll give you visual intuition as to how Cannon works. But this is quite efficient. And the syntax would be nearly the same as you saw for SimpleImputer. So we have to, instead of SimpleImputer, this time call a Cannon imputer, K nearest neighbors imputer. We have to pass a number of neighbors. This is called a hyperparameter, not a fixed value. You can try to change this. In this case, we are choosing it as 5. It depends on the end goal of our exercise. But right now, just to illustrate how this works, I'm taking a value of 5. And then I'm fitting this imputer to this data frame, which is a copy of the original data called dfcannon. And then we are doing a transform. Pretty much the same syntax as SimpleImputer. Then finally, after we do the transformation. So this is a bit of repetition here, it looks like. We seem to have written the same line twice. I'm just commenting it. We'll take it up from here. We're converting the imputed output into the data frame format and checking the specific columns which had missing values. There's a catch here. I'll show you what's wrong with this so far. But you got an idea about how Cannon works, right? So Cannon has not given the same value everywhere. So far, if you see, with the approach relative to SimpleImputer, for all the alcohol values that were missing, either we got 0 when we chose a constant, or we got a 12.86 something when we chose a median, or we got a 12.90 something when we chose a mean. But Cannon is a little smart. Cannon imputes different values at different places. Why? Because it is not looking at the overall data and looking at the overall average. It is looking at the local neighborhood of each observation and finding out 5 most similar observations, and based on their values, doing an imputation, an average here. Similarly, for ProLean, again, you can see the values are not all constant like 630 or something that we saw earlier. These are all varying depending on the similarities between the observations. Once again, if you need clarity on KNN, how does it work, you can refer to the link in the description. That's a very interesting algorithm you must know about. But there's a catch here. There's one thing that we've ignored. KNN makes its decision based on the neighbors. So in terms of decision making, KNN is not affected by the extreme values or the outliers because it only relies on the neighbors to find out the missing values. However, KNN uses Euclidean distance to find out the nearest neighbors. So in the process of finding out the nearest neighbors, it does require the data to be on the same scale. We deliberately did not do it first here because this is a common mistake a lot of people make. In the subsequent step, I'll show you the importance of scaling. Let's scroll down and see how we want to modify this a little bit and why we want to modify it. Let's take a copy of the data frame and we are calling it df outlier. Why? Because we have outliers in the data. So far, we did not check it. Let's visualize that. These are the columns and writing a simple code to get the box plots for all the features. So what we are doing is we are deciding a figure output size. Again, bit of a trial and error brings us home here. Then we are listing down the names of the features that we had in our data. All the features are listed down here. We are going over every single feature in this list, the length of this list. And then we have divided our plotting area into 3 rows and 5 columns. Why? Because we had such number of features which can be accommodated in these 3 into 5 or 15 blocks. This I+1 would represent the index of the plot. And since plt.subplot does not follow 0 indexing, we are doing an I+1. Finally, we are doing a box plot, which is the easiest way to visualize or detect the presence of outliers. Data is the same data that we just created a copy of. Finally, we are giving a dynamic title. So it will show the name of the feature and below which it will show the box plot, doing a tight layout to get a clear output, non-overlapping output. So see, we had 13 features and these could be accommodated in a grid of 15. We have 2 blanks here, that's totally fine. And now if you see, there are many features which seem to have outliers. For example, this feature, malic acid, has outliers, ash has outliers, this feature has outliers, this one has outliers, these two here have outliers. There are many features that have outliers. These names are overlapping because these were somewhat peculiar names and much longer names, so we couldn't put them any nicely, but we get an idea that there are features in our data which have outliers. Once again, why are we talking about this? KNN is not affected by outliers in decision making, but KNN does require the data to be scaled. A common scaling technique like standard scaler or min-max scaler would be affected by outliers. We've explained that at length in our video on feature scaling. In case you've not watched that, you may want to do that first. We are choosing a specific type of scaling, which is known as the robust scaling. Pretty much the same syntax as standard scaler or min-max scaler, but this is robust to the presence of outliers because it uses the interquartile range to perform scaling. So pretty much the same code. The only difference is we are going to give KNN the input, which is pre-scaled. These are the new lines of code that you see. We instantiated a robust scaler. Then we did a fit transform on the KNN dataset, a copy of the outlier dataset, and then we are generating a data frame. This data frame, which is a scale data frame, is now going to get supplied as an input to the KNN imputer. And finally, we'll be looking at the output. So this is the output. We could have zeroed down to these specific columns, but you can see alcohol had some missing values. At the first place, it had a missing value. That has been replaced with a value which is obtained from its nearest neighbors. Next, in the same sequence, there is another imputer which we must be knowing about. It is known as the iterative imputer. Now, this has been introduced in Python much later. This always used to be there in a programming language called R, and it was known as MICE, multiple imputations through chained equations. This is a very powerful imputer because it fits multiple regression models to be able to predict the missing values. See, just like you use independent features to predict a target or an outcome column, if we have everything else available in a row, but a particular feature is missing, which could be an independent feature, why can't we use the available information and predict that value? So this fits multiple regression models and tries to come up with the prediction for the missing values. The only catch is that because iterative imputer uses regression models, it is sensitive to the presence of outliers. In the earlier example, we did not treat the outliers. We found our way through them by simply choosing a scaling that would have ignored the presence of outliers. But in case of an iterative imputer, we actually need to treat the outliers because we are going to fit a regression model, and regression models are highly sensitive towards presence of outliers. So what we are doing is we are taking a copy of the outlier data frame, we're calling it df iterative, and then we are using a treatment for the outliers. What are we saying? For each feature in this data set, we are going to calculate the 25th and 75th percentile and take a difference between the 75th and 25th percentile to obtain the middle 50% data. And then the lower and upper limit for the presence of outliers are Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. Finally, wherever in our data, wherever in any feature we encounter that a given value is less than the lower limit, we are going to change it to the lower limit. This is called a flooring operation. Otherwise, we'll leave it as is. Likewise, if we encounter a value greater than the upper limit, we are going to cap it to the upper limit, else we'll leave it as is. So at the end of this execution, when we apply this, we will have treated all our outlier values. We would have brought them either to the lower limit or to the upper limit. Once we have done the outlier treatment, we can go for a common scaling technique. Because we don't have outliers anymore, we don't need a robust scaler. So we are using a standard scaler in this case, and we are doing a fit transform. Finally, the syntax for iterative imputer, it requires an input for how many iterations you want to run it for. Again, this is a hyperparameter, does not have to be 10, but we've just taken the value as 10. What would be the right value would depend on what's the end objective of what you want to achieve out of it. So if by doing this, later on you fit a model and you get good results, you probably would be happy with 10 as well. But if you do not get a good result, you might want to change this value. So in terms of syntax, we are mentioning how many iterations we want to run so that it can fit multiple models, which are all regression models, and a random state. Why is this needed? For reproducibility. If we do not mention this, we may get different outcomes every time. This ensures that whatever we did in an iterative way is reproducible. Finally, we are doing a fit transform and converting the output to a data frame, and we can again show you the head of the data. So this is the data. So remember, first value for alcohol was missing, and now you can see that's 13.41. And if we want, we can specifically filter for all those rows which had missing values, which is what we've been looking at earlier. If you remember, a value here was also missing, and this value has been again imputed using iterative imputer. And if you want to see this somewhat nicely, you can limit this output to 2 decimal places using a simple display format function. To summarize, in this video, we learned about the importance of missing value treatment right from scratch, and we did a complete hands-on covering all possibilities available within Pandas and with the Scikit-learn Imputer. Hope this gives you a good idea about missing value treatment. While this was a smaller data set, the same techniques can be applied to much complex data set. Particularly the last few imputation techniques like KNN Imputer and iterative imputers are very, very powerful. Hope this video provides you a lot more clarity on missing value treatment. Thank you.